Hello students, welcome to lecture 6 of the online course on modern display technologies, flat panel displays. Today's lecture will be on introduction to color science. So here is the lecture outline. We'll first look into the spatial and temporal characteristic of display. Then we'll move on to color science and engineering. We'll have a brief introduction and then talk about photometry, and remaining aspects we'll be covering in the next lecture. So let us first understand the spatial and temporal characteristics of display. So first let's take up the spatial characteristics. So uniformity is one of the most important characteristics of display. It basically refers to unwanted changes in luminescence or color across the display. So you don't want a display where the same image is there, you expect the same color to stay there, but suddenly the color is bright on one side and dark on the other. Right, because human eyes are sensitive to this kind of changes, and between adjacent pixels, whenever there is a 5% luminance difference, it becomes noticeable, and whenever there is a gradual change across the entire display, there is a catch. Up to 20% we are tolerable. Another important special characteristics for display is the viewing angle. So if you remember, in early days, the TVs were only viewed from particular angle, but now with time, from side angle also you should get the same feel. So that is where the viewing angle plays an important role. That means the luminance and the color should not change at oblique incidence or oblique angles. So if you see traditionally the Lambertian emitters like CRTs, they give you good viewing angle performance. How about LEDs and OLEDs? Their viewing profile can be improved with engineering. That means you can use packaging or do layer optimization so that the color and the image quality remain same at large oblique angle also. Now for LCDs, the viewing angle needs some careful management, and this is because of the nature of the display, because it is dependent on the birefringent liquid crystal materials and polarizers. So here this is quantified by the luminance threshold. You need to maintain minimum contrast ratio of something like 10:1, and there is a maximum allowable color shift. So if you have poor viewing angle, that can basically lead to contrast ratios below 1. That means you may have a gray level inversion. So LCDs have this issue to a big extent because of their nature. Now we come to the temporal characteristic of display. The first thing that should come to your mind is the response time. This basically tells you the speed of pixel transition. So what are the types of response time? The first thing is rise and fall time. So whenever you are switching from off to on and vice versa, you are basically switching between two different luminance level, that is 10% and 90%. 10% is for off, 90% is for on. So how much is the time you typically required to go from 10% to 90%? That is your on time, and other way, so that will be your fall time. Another type of response time is gray to gray, G to G, that is the transition between different gray level. So this has more representative of real world content. So when you think of the LCDs, they are basically getting driven by TFTs, which are thin film transistors. So there you need to use a set and hold voltage function to do this kind of response, unlike it is unlike in CRTs where you have this impulse response. So here there is a finite rise time and fall time. So the another concept or common metric that people use is motion picture response time, MPRT. So these are common metric that people use for this TFT LCDs. We will look into this in very much details when you go into the driving scheme of LCDs. So here we are just introducing this concept to you. Another important characteristic is the luminance decay. So, whenever there is prolonged operation of a display, this may reduce luminance, and especially this can happen in case of emissive displays. There are other issues may also come up, something like burn-in or residual image, which is a case for the OLEDs. I was telling about the problem in OLED TVs. So, this is one major drawback in OLEDs, and this happens when static images are displayed for extended period. So, here what happened, a visible faint ghost like image will start appearing on your screen whenever you are changing your screen to a blank white display. So, the static image will get basically imprinted on the display. This is called burn-in or residual image. So, what is the solution to avoid burn-in? You need to use moving images, or you look for some static images which changes over time, or some sort of static images that ensures uniform decay across all the pixels. So, note that this metrics and considerations that we described here are crucial for evaluating and optimizing the flat panel display performances in real world applications. So, having understood all these characteristics, now let us look into some more fundamental aspect of displays. What are this color? How do you get this color information? So, color science and engineering are basically essential for evaluating the performance in color image display systems. So, the perception of color basically involves 4 stages. The first thing is the light source, whether it is a natural or man-made light source that is required for the visibility. Second is the light object interaction. So, what kind of phenomena is happening there, whether there is reflection, there is absorption of the light, or the light is simply getting transmitted. Then there is eye stimulation. Any of these lights will be reaching human eye. So, this is where the photons are basically getting detected, and finally, the brain has to recognize by interpreting the signals as color. So, human eye and light interaction happens like this. You can consider sunlight as a white light source that basically covers the entire visible spectrum. Okay. So, when there is no light source, that means no photon. So, you do not even see any color, and then the final thing is any object that you see basically absorbs some photons and they reflect some. Okay. So, whatever the object is reflecting, you are basically seeing that color, those photons or that color. So, you basically perceive that is the color of that particular object. Okay. So, we can illustrate this using an example. So, if you have yellow ink on a white paper and you are sending white light, so what will happen? Only the yellow light will get reflected. So, yellow light or white light, if you split them, what it is? White light is nothing but lambda r plus lambda g plus lambda b. So, it has got red, green and blue. Now, yellow basically tells you this yellow ink will basically reflect yellow. So, that is basically red and green. So, what is happening? This is actually absorbing the blue wavelengths. Okay. Now, if you put a green ink under the same light, what will happen? So, when you put R, G and B, G will come out. So, R and B are basically getting absorbed, right. And if you have a white paper where white light is falling, so all the colors are basically getting reflected. So, that is why you see it as a white. So, this is how the color that we see, and this is how any object's color is determined. So, you can understand the color of the object basically changes with the spectral content of the light. How? Now, imagine that instead of red light, white light, you are sending red light to this yellow ink. What will happen? So, red light falling on this particular yellow ink the yellow is not going to absorb red light. Okay. So, it will basically reflect. So, it will basically look as if it is similar to this white paper. So, you are not basically able to see this. So, in short, you can say under red light this yellow ink will appear similar to the white paper. Now, let us look into the parameters of light waves. So, a light wave can be characterized by intensity, that is directly connected to the brightness. Then you have wavelength, which is important for determining the color. So, typically we are only considered about the visible range, that is from violet to red, that is 380 to 780 nanometer in wavelength. These are the vacuum wavelengths. Okay. Then the phase and polarization, typically these two things are not resolvable by human eyes. Next is human eye sensitivity. So, if we have photo receptors or photo detectors, you can say, in our eyes, that basically absorb these photons and give you this signal of what color is getting absorbed. So, photosensitive cells, which are basically cones and rods, they are able to detect different wavelengths, and that leads to color perception or cones. So, rod and cone cells are basically specialized photoreceptor neurons, okay, in the retina that basically convert light into electrical signals. So, rods are highly sensitive and they enable monochrome night vision and also peripheral detection, whereas cones are less sensitive as compared to rod, but they are specialized for high acuity color vision in bright light, and also they are mainly concentrated in the fovea region. Okay. So, what you understand is the light intensity plays an important role in the perception of brightness or darkness. Now, human eye, when you want to find out what color is it, so typically any human with a normal color vision will have three types of cone cells, each with different spectral sensitivity. So, that enables the use of three primary colors, that is red, green and blue, to generate and describe many other colors, okay, quantitatively. So, this kind of three color system is called trichromatic space. So, in 1931, this kind of system was first proposed by this International Commission of Eclairs, CIE. Okay. So, they basically proposed a method to represent all colors using distinct coordinates capital X, capital Y and capital Z. This also indicates the brightness of the object. Okay. Now, this particular system is convenient for color description, but we can see that it is limited in certain applications, like it does not quantify perceived differences between two colors, and it is designed for self luminous objects without ambient references. That means it basically limits some display applications. Now, let us go into this system 1931 CIE system in more details. So, it is the first foundational mathematical model linking physical light spectra to human color perception. So, it basically defines a standard observer to quantify color into tri-stimuli values, which are capital X, capital Y and capital Z, where capital Y basically represents the luminance. Okay. So, you understand that this tri-stimuli values X, Y, Z, the three numbers are for representing colors, okay, analogous to how human eye basically break down light. So, they are corresponding to RGB values, not directly. Okay. So, and the other thing is Y basically gives you the perceived brightness or luminance of a color. So, the system enables standardized color measurement, chromaticity, which is independent of device specific RGB values. So, what are the key aspects of this system? First is this capital X, Y, Z color space. So, these are basically imaginary primaries. These were created to avoid negative values in color matching, to ensure all visible colors are basically represented by positive values. Now, in this particular system, the standard observer, okay, it is basically based on experiments conducted at 2-degree field of view that basically only stimulates this fovea, which is very highly sensitive to the color. Okay. So, if you look into a chromaticity diagram of CIE 1931, it is nothing but a 2D visualization that maps all perceivable color or chromaticities, I should say, using small x and small y coordinates. So, these small x and small y are basically obtained from proportion. So, small x is nothing but capital X divided by capital X plus y plus z, okay. And you can also obtain, so you can obtain what is small y as well, and then you can find out the color matching functions. So, the set of functions which is small x bar lambda, small y bar lambda and small z bar lambda, this basically describes how an average eye responds to different wavelengths. That is why it is a function of lambda. So, if you take x bar, small x bar lambda, this basically represent the red primary component, y bar lambda represents the green primary, and it is also set to match the eye's sensitivity to brightness. That is how it also corresponds to luminance. And then you have small z bar lambda, that basically represents blue primary. So, what are the application? The application is that this particular system can be used to define color gamut, that means a wide range of color that it can represent, okay, and it can calibrate displays, okay. A red should look red, okay. So, you need to calibrate displays. It can measure object colors and the color temperature. So, this is how typically it looks like. It ranges from 0 to 0.8 and y is going from 0 to 0.9, and this is a horseshoe kind of pattern. So, on the periphery you can see different wavelengths written. These are basically the monochromatic light wavelengths that you can see, okay. So, 460 is blue and 460 is 620 is red, and 520 is green, where the illuminance is the highest, something like that, okay. So, while being highly successful, this 1931 CIE color space, as you can see, is not perfectly uniform, but it is a step forward that has led to 1976 CIE LUV and CIE LAB color spaces, which can better represent the perceptual differences. So, let us first look into this new system which was redone in 1976. So, these are called uniform color spaces in CIE 1976, which were basically introduced to address the limitations of the CIE 1931 system. So, it includes L star, U star, V star and L star, A star, B star spaces. So, what are these? So, CIE 1976 CIE lab LAB, okay. It is basically designed for applications that needs to measure the color differences, especially in reflected objects such as paints, textiles and plastics. So, let us see what L star look for. It is lightness. That means it represents lightness ranging from 0 that represent dark black to 100 that represent diffuse white. Then you have A star, that is representing green red. So, it is an axis that represents chromaticity. So, the negative values indicate green and the positive values indicate red or magenta. Then you have B star, that is blue yellow. Again it is another axis that represents the chromaticity. So, the negative values represent blue and the positive values represent yellow. So, what is the application? This is widely used in manufacturing and printing industries because of its intuitive and perceptually uniform nature. It is very important to understand these color systems, or else different displays cannot be calibrated. What looks like a green to you may be printed as a different green in a different system. So, there has to be some sort of measurement technique that tells you how these displays can be calibrated. The next one is CIELUV, okay, that is a variation from the previous one, which basically uses the same lightness scale as we have discussed in L star, A star and B star. But here the changes are incorporated in how the chromaticity is basically handled. Specifically, these are designed for additive color mixing between emissive sources. Okay. So, L star, as we understand, it is same as the CIE lab. Now, here you have two new things, which is U star and V star. So, both represent chromaticity because you can have U star and V star axis. So, these are basically linear transformations of the chromaticity coordinates, okay, useful for display technologies. So, when you talk about computer displays like TVs and any other additive color technologies, okay, this is the system people use because it allows easy determination of the white points. So, if you put the two systems side by side and try to highlight the key differences, you can see that this is your CIE lab and this is your CIE LUV love. Okay. So, the primary usage here is surface color. It is used for object colors, printing and paints. People use this kind of system. For light sources and display technologies, television, people use this particular system. The chromaticity axis I have already discussed, A star and B star here. Here it is U star and B star. These are basically based on linear transformation. Here A star gives you red and green. So, when negative it is red, when positive it is green, and similarly for B star, when negative it is blue. Okay, I think it is other way around. Yeah. So, negative is green, positive is red. Here also negative is blue, positive is yellow, okay, for B star. Now, how about the uniformity? This scheme is good, but somewhat non-uniform in certain ranges. However, if you consider CIE LUV, they are good, particularly suitable for additive color mixing. And uniformity base, these are based on Adamson-Nicholson space. This is based on McAdams findings for chromaticity. This is not that important right now. So, here you can use you can understand the basic comparison between the two schemes. So, if you want to summarize, what do you understand, that 1976 CIE uniform color spaces, the key features are that it allows specification of numerical color differences between two colors. It ensures just distinguishable color differences are consistent across diagrams between similar greenish and reddish colors. So, the color production in displays, as we understood, you require trichromatic space to quantitatively describe using these CIE systems, so that the colors can be produced or reproduced in display devices by mixing the three primary emitters. Then there is metamerism. This is basically a phenomena where different spectral power distribution could produce identical perceived colors. Okay? So, this basically enables the human visual system to perceive a real object and its display representation as the same color despite their reflection spectra looks very different. So, that is called metamerism. So, with that we understood what are the colorimetry and the color codes in place. Now, let us go into photometry, how we measure light. So, the perception of brightness is the first thing, right. So, the human eye's spectral sensitivity influences brightness perception of light sources with identical optical power, okay, in watts at different wavelengths. For human eye, the sensitivity basically peaks at 555 nanometer, that is basically in the green region, which is defined by V lambda, okay, under photopic vision. Now, photometric units and luminous flux. So, the first important parameter that we need to understand is lumen. So, when I say 1 lumen, this is basically the 1 luminous flux that is coming from 1 by 683 watt of monochromatic light at 555 nanometer. So, this is the standard definition of 1 lumen. Okay. So, example, if you have a different wavelength, that is 650 nanometer, and if V lambda is 0.1, that means you basically require 1/10 of this kind of power to achieve 1 lumen, right. So, 1/10 of this power is basically 1 over 68.3 watt, right. Next is candela. Now, what is candela? It is a primary photometric unit which is basically defined as 1 lumen per steradian. That means steradian is the unit of the solid angle. Okay. So, this basically represents the luminous intensity. Okay. So, initially it is based on the luminous intensity of standardized candle. So, here is how the conceptual flow of light and perception takes place. So, you have a light source here, a candle, okay, that basically emits luminous flux in all direction, right. And now, human eye basically perceives this luminous intensity within a limited solid angle which is known as steradian. So, you are getting lumen per steradian, that is your luminous intensity. Now, if there is an object nearby, this light is going to illuminate the object as well, and it is going to be modulated by the object, either it is getting to be reflected, transmitted or absorbed or scattered. So, what happens after modulation? This modulated light basically re-enters as luminous excitance, okay, from this particular object. So, this object is also getting the light, so it is getting illuminated. So, this is called illuminance, which is lumen per square meter that you get to see here, okay. And whatever is seen by the eye, okay, that is within this solid angle. So, it is illuminance per solid angle. So, it is becoming luminance, which is lumen per steradian times meter square. So, here are the 3 important parameters. One is illuminance. This is basically the light intensity on a surface which is measured in lux, which is lumen per meter square. Okay. Then you have luminous excitance, which is M, that is basically the apparent emission from an object, which is again measured in terms of lux. Okay. And luminance is the perceived brightness of an object that is captured by the eye. So, here the solid angle will get into picture. So, it is basically candela per meter square or nits. So, this is the perceived brightness units, nits or candela per meter square. So, in summary, you can see these are the photometric units people use. So, you have luminous flux which is coming out from this candle. The symbol is F, because it's flux. So, unit is lumen, LM. Okay. Then you have luminous intensity, which is seen by the eye. So, that is intensity is I, the unit will be lumen per steradian. So, the unit is candela. You have illuminance which is M, which is basically lumen per meter square, which is lux. The same thing also exit here. So, that is luminous excitance E. So, this is basically E, which is again same lumen per meter square or lux, and this is your luminance, what is perceived by the eye. So, that is again symbol is L, its unit is nits, which is candela per meter square. So, these are the different photometric units people use for defining the light in a display system. So, with that we conclude today's lecture. If you have any query, you can drop an email to this email address mentioning the subject name, the course name on the subject line. Thank you.